Recording. Okay, so exit that. All right, so moving on, we got to talk about titrations. That's like the most important thing in this chapter because you're going to see this again if you take quant or a higher level chemistry class. So an acid-base titration is a way of determining the concentration of your original solution. Okay, so titrations are important and they're done a lot in quantitative analysis in order to determine the concentration of your original acid or base. Okay, so a solution of unknown concentration is slowly added to a solution of known concentration until the reaction is complete, and that completion is determined either by the pH with a pH meter, or it's determined by colorimetric analysis, like using a indicator. Okay, so when the moles of acid are stoichiometrically equal to the moles of base, the titration has reached its equivalence point, and we'll talk about that in a few minutes. An indicator is often used, and that gives us a color change when the pH changes. So it tells you what pH, pretty close to what pH you're at by the color. So if you have a base in your, this thing is called a burette, this tall test tube looking thing with this on the bottom is called a stopcock. Okay, so you're probably doing titrations in lab now, and so you'll put an unknown concentration. You have an unknown concentration here, and so you're going to drop your solution of known concentration from the top, and until you reach an equivalence point, which is often indicated by a change in color. And this equivalence point occurs pretty close to neutral. And then if you know the concentration of one of the solutions, you can back calculate the concentration of the other. When that titration ends, your color will change, or rather when the color changes, your titration is done, and you have equivalent moles of the starting solution and the final solution. Okay, so a titration curve is a plot of pH versus the amount of titrant added. So you would use a pH meter if you're going to do a titration curve. An inflection point, we're going to see a plot in just a minute. An inflection point of the curve is the equivalence point of the titration, so the center of that inflection point. Prior to the equivalence point, the original solution in the flask is in excess, so the pH is closest to the pH. I don't even know what they're talking about here. Let's look at what the curve looks like. So here at the low, in this case, we are starting with an acid of unknown concentration. So acid here. All right, and so we've got a low pH because we have an acid. So we're plotting pH versus volume of sodium hydroxide added. Okay, and so as we add more sodium hydroxide, the pH is going to begin to change. So if we add, so this would be 10, 20, 30, 40 milliliters. So this is some theoretical concentration of sodium hydroxide, like say 1 molar or whatever. All right, and so if you add 10 milliliters, it's going to increase the pH a little bit, 20, 30, 40, okay? And so notice that at some point, the pH begins to increase rapidly, and that's our inflection point. So at the center of that inflection is the equivalence point, and that's the point where the moles of acid equals the moles of base. Okay, and so we also have what's called a half equivalence point. Okay, so if this is 50, then our half equivalence point is going to be at 25. Okay, and the half equivalence point has a special property as well. That's where we've got, that is where we have the pH equal to the pKa, and we're going to see that in just a few minutes. All right, and so if the titration is run so that the base in the flask and you're adding acid, then you're going to have an opposite situation here where you're starting with a high pH and you're ending up with a low pH, and your equivalence point will still be similar, but your curve is opposite. So titrating a weak acid with a strong base results in differences in the titration curve and the excess acid region and the equivalence point. Okay, so we're going to see titrating something like a strong base. Let's back up a little bit. Titrating a strong base with a strong acid, you can just calculate how much of either acid or base you have left over. So we're going to look at some examples of that. If you have a weak acid with a strong base, then once you run out of strong base, if you have weak acid left over, then you have to calculate your pH as an equilibrium problem, okay? If you titrate a weak base with a strong acid, then once you run out of acid, you'll have the weak base left over, and you calculate your pH as an equilibrium problem. So the initial pH is determined using the Ka of the weak acid, and that's before you add any of the strong base in there. The pH in the excess acid region is determined as you would determine the pH of a buffer. So we're going to look at how to do those kinds of problems. Okay, so the amount of strong acid in the flask shown here is to be titrated by a strong base, which mark on the burette next to the flask indicates the amount of base required to reach the equivalence point. Okay, so if we've got 1, 2, 3, 4, 5, 6, 7 molecules of acid, we've got 1, 2, 3, 4, 5, 6, 7 molecules of base. That would be D. All right, so here's a weak acid with a strong base. We've got a little bit different curve here. Okay, so we've still got an acid, so we have a low pH going to a high pH. So as we begin to add more sodium hydroxide, our pH begins to increase until we reach this inflection point. But notice it's not quite as strong. This is our equivalence point where we have equal moles of acid and base. Okay. All right, so first we have to work a stoichiometry problem, and then we have to work a equilibrium problem, kind of like what we did before when we do these titration problems. So we're going to look at how that works in just a few minutes. Okay. I looked at all of these PowerPoints last week, and now they have all kind of slipped my mind. So I kind of apologize for blowing over them, but I thought I would remember them pretty well, but I should have looked over them like last night. So if you have a weak acid and a strong base, then what you end up with is before the equivalence point, you end up with a buffer. So basically, when you're working a titration problem, you have to look at what region you're in on this graph, okay? So at this point, at pH 7, you're going to be neutral. And whether at the equivalence point you're going to be, you're usually at the equivalence point, you're going to be somewhere around neutral, but it isn't always going to be neutral. And that's because you might have some conjugate base of the acid hanging around, like in this case, we have some conjugate base of the acid. And so that's going to increase our pH and make the pH a little bit basic. So if you're in the acid region, you're going to be finding the pH by determining what your H plus concentration is and then take the negative log of that. Okay. If you're in the basic region, then you're going to find your pH by calculating your hydroxide ion concentration. And then you can take the negative log of that. That will be your POH, and you can calculate your pH from that. So you have to, the thing that makes titrations more complicated is because you have to look at what region of the chart you're in and think about what you're going to end up with Okay, and then that's the way you calculate your pH. So you have to determine your pH by what region of the titration plot you would be in if you did that particular reaction or you added that amount of acid or base, and then you figure out how you're going to calculate your pH from there. So it requires a little bit more thought rather than just straightforward working a problem. And that's what makes the titration problems a little bit more challenging. Um, so before the equivalence point, the solution becomes a buffer, and you're going to calculate your amount of acid you have using reaction stoichiometry, and then you do an equilibrium problem to calculate the pH. You can use the Henderson-Hasselbalch equation. Now you can also use the equilibrium method if you want to, but as long as you can make your X is small approximation, meaning that you have a weak acid, in this case you have a weak acid or a weak base, then you can use the Henderson-Hasselbalch equation to determine the pH. Now, I've thrown a lot of information at you, so let me back up a little bit. So we're going to work some titration problems, okay? So the first kind of titration problem we're going to work is either a strong base with a strong acid or a strong acid with a strong base. So in order to do these kinds of problems, all you have to do is calculate how much reacted, and then you figure out what region of the graph you're going to be in to calculate whether you're going to use to determine whether you're going to use the H plus or the OH minus concentration to determine your pH. So this is going to be a reaction like, let's say HCl plus sodium hydroxide gives you sodium chloride plus water. Okay, because acid plus base gives you a salt plus water. And since this is a strong acid and a strong base, and this is a 1-to-1 ratio, okay, you can use those amounts to determine whether you're going to have more H plus or more OH minus, or let's just say if you added 1 mole of this and 1 mole of this, okay, then you're going to end up with just 1 mole of sodium chloride and 1 mole of water. Okay, so at that point you would be at the equivalence point. Okay, so you would be at a pH of 7 in this case, because you just have a salt plus water. You don't have a weak base or the anion of a weak acid or the anion of a weak base to worry about. So if you have a strong base and a strong acid, you react equal amounts of those together, you're going to end up with a pH neutral solution. Okay, and if let's say that, for example, we reacted a half a mole of this, a half a mole of this with 1 mole of this, we got a 1-to-1 ratio here. So what are we going to end up in the end? We're going to end up with some salt and some water, and we're also going to still have some sodium hydroxide floating around. So we're going to have more hydroxide, okay? So we're going to be in the basic range, and we're going to have to calculate the POH. But if we reacted, change colors here, 1 mole of HCl with, let's say, a half mole of sodium hydroxide, then we're going to form some salt and water, but we're also going to have more H plus hanging around. So to calculate the pH, we're going to use the the H3O plus concentration, or the H plus concentration, and we're going to calculate the pH directly from there, taking the negative log of that. So if you've got a strong acid and a strong base added together, you're going to have a salt plus water form that's going to give you a neutral product, but then whichever of the H plus or OH minus in excess, if that happens, then you have to use that to calculate your pH. Hopefully this makes sense. Okay, so that same thing with a strong base and a strong acid. You're going to have those guys reacting together to give you neutral products, but then you could have one either H plus or OH minus in excess. okay, at the end of your reaction. And then you're going to use either the hydroxide or the H plus concentration to calculate your pH. And we're going to do some examples of that in just a minute. Okay, but then if you have a weak acid and a strong base, or a weak base and a strong acid, let's look at that example. So let's say that we have, I always forget how they write this. CH3COOH is acetic acid. So that would be HC2H3O2, right? All right, plus, so this is our acid. Let's say we're adding sodium hydroxide to this. So what are we going to end up with? We're going to end up with the acetate anion. Okay, so what's going to happen here? This OH minus is going to pull off this H plus, and we're going to end up with water. Okay, and when this H plus is pulled off, we end up with the acetate anion, C2H3O2, and we have Na plus as the counter ion. Okay, so that's our reaction. Now, this conjugate base here, okay, this conjugate base acetate, okay, this is a reversible reaction. So when we get acetate in solution, that's not neutral. So because that thing is going to start pulling hydrogens off and forming an equilibrium and going back the other way. So we have to consider an equilibrium problem. So when we use an acid with a strong base, first we have to do a stoichiometry problem, and then we have to work an equilibrium problem. And the equilibrium problem is done with the Henderson-Hasselbalch equation using the Ka. Okay, and so we'll look at some examples of that. But let's say that we have 1 mole of this, and I'm oversimplifying here, and a half mole of this, okay? That sodium hydroxide is a strong base. It's going to be strong enough, okay, to pull off a full half mole of hydrogens, okay? So then we're going to end up with a half mole of acetate coming from the reaction, okay, but we've still got our equilibrium where we have the HC2H3O2 forming H plus C2H3O2 just from ionization. So in the first step, we work a stoichiometry problem, which gives us this information. And in the second step, we work an equilibrium problem that also takes into account this reaction as well, okay? So let's just go ahead and work some problems with this rather than dwelling on these PowerPoints, which I don't think explain it all that well anyway. I think it'd be better just to jump in and try to work some problems. Okay, so that left us with 18.4, which is actually using the Henderson-Hasselbalch equation to calculate the pH of a buffer solution. So let's go back to our PowerPoints here. So what are we doing? When we titrate a weak acid with a strong base, or a weak base with a strong acid, then we're actually forming a buffer solution, okay? I was going back to the PowerPoints I just drew. Okay, so we're forming a buffer solution, and because of that, we can use the Henderson-Hasselbalch equation to calculate that equilibrium problem. So this, at this point, is actually a buffer. So to prepare for that, your book is having you do some buffer calculations in order to understand what's going on. So what I'm going to do is blow through the example here by what they've shown, and then I'll work the for practice problem, okay? So using the Henderson-Hasselbalch equation, which is fairly straightforward, calculate the pH of a buffer solution that is a half molar in ammonia. and 0.2 molar in ammonium chloride. For ammonia, the pKb is 4.75. Okay, so ammonia is a base, not an acid. Okay, but the Henderson-Hasselbalch equation says that the pH is equal to the pKa, not the pKb, the pKa, plus the log of the base over the acid concentration. That's in concentration units here, not moles, okay? So we don't need the pKa, we need the pKb. So the first thing we got to do is calculate the pKb from the pKa from the pK. We don't need the pKb, we need the pKa. So we got to calculate the pKa from the pKb. So we can get that by saying 14 minus the pKb is the pKa. So 14 minus 4.75 is 9.25, okay? So using the Henderson-Hasselbalch equation, we can just plug in. Okay, so we have a half molar in ammonia and 0.2 molar in ammonium chloride. So 9.25 plus the log of a half over 0.2, 9.25 plus 0.4 is 9.65. So that problem is fairly straightforward, okay? So for practice 18.4, I'm going to go ahead and work for you. All right, find my notes. All right, and so calculate the pH of 1 liter of the solution in 18.4 upon the addition of 0.010 molar solid sodium hydroxide to the original buffer solution. Okay, so 18.4 was, let's do this right here. So 0.50 molar NH3 and 0.20 molar NH4Cl. Okay, pKb is equal to 4.75, and pKa is equal to 9.25. Okay, so how are we going to work this problem? So now we're not saying I've just got this buffer solution, I want to use the Henderson-Hasselbalch equation. What I got to do now is work 1, a stoichiometry problem, and 2, I'm going to use the Henderson-Hasselbalch equation to do an equilibrium problem. Okay, so let's make our stoichiometry table. Now this is not an ice table, this is a stoichiometry table. So because of that, we don't use molar units, we use moles. Okay, so writing our reaction, we've got OH minus, okay, that's our hydroxide from the sodium hydroxide, plus HC2 H3O2 goes to, and this is really a one-way arrow because sodium hydroxide is strong and acetate is weak. Okay, it goes to H2O plus C2 H3O2 minus. By the way, I'm taking my computer in today to get it looked at because I've had all this trouble with it because it's getting hot. Okay, so we've got our before addition, and after addition. Okay, so those are the conditions here. Okay, so before addition, we've got, let's go ahead and draw all our lines here. We don't care about the water, okay, because it's a liquid. All right, so we're starting out with about 0 moles of the hydroxide and 0.20 moles of this and 0.50 moles of this. Okay, so let's back up a minute. We've got a 1 liter solution. So if we had 0.5 molar, that's 0.5 moles per liter. That means we've got 0.50 moles of ammonia and 0.20 moles of ammonium chloride. Okay, And, well, wait a minute. This is the solution in 18.4 original buffer solution. Wait a minute, what? This is ammonia and ammonium chloride. But in my notes, I've got, I don't know why I got acetic acid here, but that's what the notes have got. So I got that. That's not supposed to be acetic acid. Wait a minute. That would be ammonia. Example 18.4. Upon the addition of 0.10 moles of solid sodium hydroxide. 18.4 is ammonia and ammonium chloride. So there must be some kind of error in here because it's telling me it's supposed to be acetic acid. If you add ammonia to, if you add sodium hydroxide to a base, you aren't accomplishing anything. Okay. So this is supposed to be acetic acid. See? So I'm just going to go with that because the books, the teacher's manual says it's supposed to be acetic acid here. So apparently there's an error in here. They changed it from ammonia to acetic acid. Okay, so let's rewrite this problem. Okay, let's say, because the ammonia wouldn't make any sense because that would be adding a base to a base. It's really weird. pKa. But they've got the pKa of 9.25. That doesn't make any sense. Okay, I don't know what's going on here. This makes no sense. I just caught this. I looked over these problems last night. The pKa for acetate, for acetic acid, is not 9.25, but they've got it down here as 9.25. Huh. But that makes no sense. I'm trying to see if I'm just looking at it wrong. I don't know. All right. I'm going to assume, so they're saying acetic acid here. I'm going to assume we've got acetic acid. So let's say we've got 0.50 moles of acetate, because that's what they're saying on this example, and 0.20 moles of acetic acid. So let's rewrite this problem. A buffer solution with 0.50 molar, so let's say a 1 liter buffer solution with 0.50 molar sodium acetate. Okay, and 0.20 molar acetic acid. Okay, so sodium acetate and acetic acid. Okay, so that means that we've got, I don't know what they're doing here. They're confused. All right, so that means that if we had a 1 liter solution, then we would have 0.50 moles of acetate, okay, and 0.20 moles of acetic acid. So we're adding sodium hydroxide to that, so we're going to work an equilibrium problem, okay? So working an equilibrium problem, the first thing we do is we say that 0.010 moles we're adding of the solid sodium hydroxide. Okay, so we're adding sodium hydroxide. So that's going to take away this much H plus. So we're going to be losing this much H plus, but we don't draw like a minus here because you can end up with negative numbers if you do that. So we just draw a line through there and we say we've got 0.19 moles of this left. And we're going to use up all of our sodium hydroxide, so we got about 0 of that. That's going to give us 0.51 moles of the acetate, because for every of the hydrogens we lose off of the acetic acid, we're going to gain 1 acetate. So we're going up by this of the acetate. Okay, we're going up by this. All right. So now we can work a stoichiometry problem. We can say the pH, I'm working equilibrium problem, is equal to the pKa for acetic acid plus the log of the base over the acid. So that's A minus over HA. All right, and so I don't have the pKa. I think it's 4.75. Yeah, that's it. The pH is equal to, I'm going to look this up real quick. I'm pretty sure it's 4.75. I'm sure it's 4.75, but I'm going to look it up anyway. pKa for acetic acid. And that's 4.76, okay? So I'm just going to work this problem because the study guide got it mixed up. I don't know what they did. 4.76 plus the log of the concentration of A minus over HA. Okay, so we've got a 1 liter solution. So that means that if we have 0.19 moles of HA, which is right here, divided by 1 liter, we're going to have 0.19 molar. And if we have 0.15 moles, that's going to give us 0.51 molar, okay, because we're dividing it by 1 liter, because that's our solution. So that is 0.51 divided by 0.19, okay, which is going to be 4.76 plus the log of, I gotta work this out because I don't have it, 0.51 divided by 0.19 equals the log of 2.68, which is equal to, take the log, 0.42 plus 4.76 is equal to 5.189. Okay, so so you can see that the pH went up a little bit, which makes sense because we're adding sodium hydroxide. So I kind of had to rewrite that that problem. So the next one, let me see if they're doing acetate or if they're doing ammonia. They're doing acetate. Okay, so we're going to work it like we're adding. So for more practice, 18.4, calculate the pH of 1 liter of the solution in 18.4 upon the addition of 30 milliliters of 1 molar HCl to the original buffer. Okay, so first we work kind of an equilibrium problem here. All right, 30 milliliters of 1 molar HCl is like this. We got moles of HCl, I probably should have worked it the other way, equals 1 mole of HCl per 1,000 milliliters. And we got 30 milliliters. All right, so that's equal to 0.030 moles of HCl. So all we're going to be doing here is adding acid. So what happens if we add acid to this solution? It's going to react with the acetate. It's going to react, if we add acid here, it's going to react with the acetate and drive this reaction back in the other direction. So we're adding this acid to the original buffer. Okay, to the original buffer. Goes to H2O plus HC2H3O2. Okay, in our original buffer, we had 0. Let me change colors. 0.20 moles of this acetic acid and 0.50 moles of this. So if we set up a table, that's before the addition and then the after addition. All right, so we had 0.50 of this, we had 0.20 of this, and so we're adding 0.30 of H plus. So that's going to give us 0 in the end of the H plus and 0.47. That's 030. Okay, 0.030 moles of HCl. 0.47 moles of acetate left, okay, because the HCl is going to react. This is a strong acid. So for every 1 mole, we're going to protonate 1 mole of that acetate, and this is a one-way reaction. Okay, and then we've got 0.23 moles of the acetic acid. Okay, so the acid can react with the conjugate base of the acetate and drive it back in the other direction. Okay, so we've got, then we can use our equilibrium problem. pH is equal to the pKa plus the log of the base over the acid. My computer is overheating again. I'm sorry. It's not working. Is equal to, and our pKa for acetic acid here is 4.76. So I'm going to have to work this problem out. So that's going to be 4.76 plus the log of 0.47 over 0.23. Is that right? Calculate the pH of a 1 liter solution upon the addition of 30 milliliters of, no, that's not right. They didn't even do that part right. We can't use that. Oh, let me back up. Okay, so we had a 1 liter solution in our original buffer. So we had 0.50 molar of this, 0.20 molar of this. That was our original buffer. So we've got 0.5 moles of this and 0.2 moles of this. Okay, but we added 30 milliliters of the sodium hydroxide solution, right? 30 milliliters of 1 molar, I'm sorry, hydrochloric acid solution. So we have to say that we've got, for the acetate, we've got 0.47. So the concentration of the acetate is equal to 0.47. That's what we ended up with, divided by 1 liter plus 0.03, so 30 milliliters is, 1, 2, 3, right, 0.030 liters, right? All right, and so that's going to be equal to what? 0.47 divided by 1. Shouldn't that be 1.3? 30 milliliters. 1, 2, 3. That's 0.03. So 1.030 liters equals 0.47 divided by 1.03, because this has to be in concentration, is equal to 0.4563 molar. Okay, that's concentration. So now we've got 0.23 moles of acid over here. 0.23 moles divided by, and it's in this solution, so 1.030 liters equals 0.23 divided by 1.030 equals 0.223 molar. All right, so now we know the concentration of the acid and the conjugate base after the addition. So now we have to do an equilibrium problem and calculate that. So the pH is equal to the pKa plus the log of A minus over HA concentration is equal to 4.76 plus the log of our A minus is right here, that's the 0.47 or 0.4563 over HA, which is 0.223, which is equal to, let's get that, 0.4563 divided by 0.223 equals plus did I get that backwards? So I'm getting 6.8, and that's not right. So A minus is 0.47, that's the 0.5, 0.23, all right, 7/6 log 0.4563 divided by 0.223. So take the, oh, okay, I didn't do that. Plus 4.76 equals, so I still got 5.07. So we added acid, and the acid reacted with the acetate to give us the water plus the undissociated acid, driving the equilibrium back in the opposite direction. Okay. So we got a very small change in the pH. All right, I'm gonna have to look into this one because that one does not seem correct to me. 0.4563 divided by 0.223 moles log. I'm thinking those numbers might be backwards. 4, 7. Oh, that's the problem. Yeah. This is our base and this is our acid. I got my numbers upside down. I knew there was something wrong here. Okay. So that's why it's important to kind of rationalize is what you're doing correct. So here's my base. That's my base is the 0.47 and the acid, no, that's right. That was 0.4563 over 0.223. 0.4563, 0.223. Huh. And let me think about this. So adding that, subtracting that, should be right. 0.4563 divided by 0.223 plus 4.76 log 5.07. So that's not right. I don't know what I did wrong here. Maybe you guys can figure it out and send me an email. Maybe I'm making a simple mistake here. I don't know. But anyway, I've got to let them know that they've got an error on their PowerPoints because they have totally a wrong thing down there. So that's actually, I don't know what I did wrong here, but that's not correct. All right, so preparing a buffer, I'm going to have to just move on. Maybe I'll figure that out and post a correction video later. I'll have to look into it. Preparing a buffer, okay? So we can't sit on that all day. All right, so preparing a buffer is fairly straightforward and the calculation is not all that difficult. All right, so which acid would you choose to combine with the sodium salt to make a buffered solution at 4.25 pH? Okay, so the best choice is going to be if you want to make a buffer and you want the buffered solution to have a pH of 4.25, you want to choose an acid that has a pKa of approximately the same pH. So the pKa of 3.74 for formic acid is going to be the closest one to the 4.25. So that's the one we're going to choose. So the pKa for formic acid is 3.74. So we're going to just plug that in, okay? And so the question is, for the best choice, calculate the ratio of conjugate base to acid required to attain the desired pH. Okay, so we got our pH we want of 4.25. Plug that in here. pKa of 3.74. So then we could just calculate the ratio. Okay, so we can just subtract 3.74 from 4.25 and say the log of base to acid is equal to 0.51, and then we can get that ratio by saying, getting rid of the log by saying taking the 10 to the power of both sides. 10 to the 0.51 is 3.24. So this is our base to acid ratio that we want. Okay, so I'm going to work the four more practice problem here. 4 more practice 18.5. Which acid in example 18.5 would you choose to create a buffer with pH 7.35 if you have 500 milliliters of a 0.1 molar solution of the acid? What mass of the corresponding sodium salt of the conjugate base do you need to make the buffer? So this one is going to be a little bit more complicated, and again there were errors, so I had to go back and rework this problem. Okay, So let's see how we can do this one. Okay, so first of all, we have pH of 7.35. So the closest pH is going to be the 7.54. So we're going to make a hypochlorous acid solution. Okay, I'm going to have to move over to the grid notes. So I've got 500 milliliters of a 0.1 molar solution of the acid. Okay, so I'm not showing where I calculated that. Oh yeah, okay, so we're going to start out with pH is equal to the pKa plus the log of the base over the acid, the concentration of base over acid. All right, and so that's going to be 7.35 is our pH is equal to 7.54 plus the log of the concentration of base to acid. I'm just going to write B over A because my computer's acting up. All right, so the log of the base over the acid is equal to 7.35 minus 7.5. That's not 5.1, that's 5.4. Thing's not working. 7.54 equals negative 0.19. Okay. So the concentration of base over acid is equal to 10 to the negative 0.19, which is equal to 0.64565. Okay? So that's our ratio that we need to get, that's the ratio that we need to achieve to get the desired pH. Okay? So again, the Henderson-Hasselbalch equation says the pH is equal to the pKa plus the log of the base over the acid. Okay, we want a buffer solution with a pH of 7.35. We have 500 milliliters of a 0.1 molar solution of the acid. What corresponding mass of the sodium salt do we need to make the buffer? Okay, so we know that we need this ratio. Okay, so if we have that ratio, then we can say the base, so we could solve for the base, the concentration of the base is equal to 0.64565 times the concentration of the acid. All right, so the base is equal to 0.64565 times the concentration of the acid is 0.10 molar. Okay, so I know that from here. The concentration of the acid is 0.10 molar. All right, and so that means that the concentration of my base is going to be equal to 0.06455 moles per liter. All right, and I need 500 milliliters of it. So because my computer is not writing well, I'm just going to put it right here. All right, so 0.500 liters, okay? And so that's going to give me 0.032285 moles. All right, and so the way I need to calculate, so I need this many moles to put into my solution to give me the pH that I need, the moles of my sodium salt, okay? So then I can just say 0.0322885 0.825 times 77.44, okay, grams per mole. So I get that from the periodic table, or you could just look up the molecular weight of it, of sodium ClO, sodium chlorate, or sodium hypochlorate, because we've got hypochlorous acid, all right, is equal to 2.5 grams. So in order to make this solution with 500 milliliters of my 0.1 molar acid solution, hypochlorous acid, I need to add 2.5 milliliters of sodium hypochlorite to give me the pH that I wanted, the desired pH, okay, which was 7.35. So from the Henderson-Hasselbalch equation, I knew the concentration of my acid. I can calculate how much base I need to add by first calculating the concentration of the base from the Henderson-Hasselbalch equation, and then calculating the amount here that I had, okay, and then I know how much from that many moles I can calculate the grams of the salt that I needed to add to get that pH, okay. So this was just a back calculation. All right, now we're finally getting to titrations, which I don't know if I'm even going to be able to do because my computer is not cooperating. All right, so strong acid, strong base, titration pH curve. All right, so remember we talked about this. When you're titrating a strong acid with a strong base, you don't have to work the equilibrium problem, because you just have to figure out what area of the curve you're going to be in. So here we have a 50 milliliter sample of 0.2 molar sodium hydroxide, okay, is titrated with 0.2 molar nitric acid. Calculate the pH after adding 30 milliliters of nitric acid and at the equivalent point, okay? So before the addition, we're going to have hydroxide. So here's our reaction. Hydroxide plus H3O plus goes to 2H2O. So before the addition, we have primarily hydroxide, okay, and we don't have any acid in there. So if we wanted to calculate the pH before the addition, we'd have to use the POH and then calculate the pH from that. Next, we're going to add 0.00600 moles of the H plus, okay, and so then we're going to calculate how much of the hydroxide we have left. So in this case, we didn't take away all of our hydroxide. So let's back up and look at this on a chart. So at the beginning, we've got a 50 milliliter sample of 0.2 molar sodium hydroxide. So we're going to be starting, if we have pH versus volume of acid, we're going to be starting in the high pH region and going to the low pH region, okay? So if we're at high pH, so let's say that this is pH of 7, okay, anything in this range is going to be acid. So we would use the pH is equal to the negative log of H plus. Anything in this range is going to be base, so we would use pH is equal to negative log of OH concentration, right? All right, so we're starting out with sodium hydroxide. So we're going to be at high pH, and we're going to titrate with nitric acid. So the pH is going to be going down, okay? So first we have to calculate the concentration, okay? So begin by calculating the calculate the moles from the concentration. So the moles of sodium hydroxide that we have in our flask. So let's look at what that flask looks like. So we're calculating here. We've got a flask down here with sodium hydroxide, and we're adding acid to it. Okay, so we don't know the concentration. We know how much acid we're adding, and we know how much base we had. All we have to do is calculate the pH. So this is pretty simple. So first, we have to calculate how many moles of sodium hydroxide we had. Okay, and then we're going to add how many moles of nitric acid that reacted with. Then we have to see if we're going to be in the base range or the acid range. Okay, so first we calculate the moles of sodium hydroxide. So we take 0.0500 liters times 0.2 moles per liter. That gives me 0.01 moles of sodium hydroxide. So that gives me 0.0100 moles of hydroxide ions, because remember, sodium hydroxide is going to completely dissociate, where we're going to have Na plus OH minus. Okay, so if we have 0.0100 moles of sodium hydroxide, we have 0.0100 moles of hydroxide. Now that's in our flask that we're starting with, okay? So we're going to add nitric acid to that. So we need to calculate how many moles of nitric acid. So at 0.0300 liters, at 2 moles per liter, that gives us 0.00600 moles of nitric acid. Okay. So before the addition, we had this much hydroxide, then we're adding this much acid, okay? And so we subtract this from the hydroxide. So we're subtracting the acid from the hydroxide because the acid is going to react with it. So we're going to have, let's just write the overall reaction. OH minus plus H plus goes to H2O, okay? So in this case, so let's say H3O plus, we get 2 H2O, okay? So since the H2O is a liquid, we don't care about it anyway. So we're starting with 0.0100 moles of hydroxide. We're going to add H3O plus, 0.00600. So 0.006 is less than 0.0100. So we know that we're still going to be in the base range, okay, because we're still going to have some base hanging around because we started out with more base than we had acid. So we're going to subtract the acid amount from the base that we started with. After the addition, we have 0.0040 moles of base. Now, we don't have to work an equilibrium problem here, because we know how much hydroxide we have left. We haven't reached the equivalence point yet, because at the equivalence point, we're going to have exactly the same amount of hydroxide and H+. So we're still somewhere in this base range. So we're going to have to calculate the pOH as negative log of the hydroxide concentration. I meant to say pOH is the negative log of the hydroxide, and then the pH is equal to 14 minus the pOH. Okay, so we know that we had 0.0040 moles of hydroxide, and we have the total solution volume of 0.0500 liters plus 0.0300 liters is equal to 0.004 over 0.08. So that's going to give me 0.0500 molar for my hydroxide ion concentration. So the pOH is the negative log of 0.05, which is equal to 1.3. Subtract that from 14, and I get a pH of 12.7. That makes sense because I'm still in the base range here. So I'm going to be able to calculate the pH from the pOH in the base range. At the equivalence point, the strong base has completely neutralized the strong acid, so this is part B, and our pH will be equal to 7. Okay, at the equivalence point, we're going to have all of the bases reacted with an equal amount of acid. Since it's a strong acid, strong base, we're going to have just the salt plus water formed. And so all of our H plus is just due to the autoionization of water, which is going to give us 1 times 10 to the minus 7. And the pH will be 7 at the equivalence point. Hopefully this makes sense. Past couple of days, I think I have just botched everything, and I'm sorry about that. Okay, so I'm going to move on to calculate the pH in a titration in example 18.6 after the addition of 60 milliliters of the nitric acid. Okay, so we're going to start with the same amount that we had of the original solution. Okay, so I have how much hydroxide. Okay, so a 50 milliliter sample of 0.2 molar sodium hydroxide. Okay, and that's what we started with, and we're going to titrate that. After the addition of 60 milliliters of 0.2 molar nitric acid. Okay, so 50 milliliters, let's just start over, of 0.2 molar nitric acid. Okay, and so how many moles does that give us? We already calculated that. So that's 0.0500 liters times, I'm just going to do it again, 0.200 moles per liter equals 0.0100. This is from our original solution, moles of NaOH, which is equal to 0.0100 moles of hydroxide. Okay, so this is the amount of hydroxide that we're starting with. I can't even write anymore on this thing. Okay, so we have to set up our table, but first we need to calculate the moles of nitric acid we had. So we had, after 60 milliliters of 0.2 molar nitric acid. So that would be 0.200 moles of HNO3 per 1,000 milliliters times 60 milliliters equals 0.0120 moles of nitric acid. Okay, so now we're reacting this much hydroxide with this much nitric acid. So what do you think is going to happen? So we've got this reaction. This is strong acid, strong base. Hydroxide plus H3O plus goes to 2H2O. Okay, and so we could set up our table, and we're starting out with we're starting out with 0.01 moles of hydroxide. All right, and then we're adding 0.0120 moles of the nitric acid. Okay, so this is before addition, addition, after addition. Okay. All right, so what's that going to give us? We're going to end up with 0.0120. We're going to end up with more H plus at the end. We're going to end up with 0.002 moles of H plus in excess. Okay, so you can see that the H plus is greater than the OH minus. Okay, so we're adding this. We're going to end up with 0.002 of excess of the H3O plus because of this reaction. Okay, so there's still going to be some extra of this hanging around. So that's how we're going to calculate our pH. Okay. All right, so we have to say that we got 0.002 moles of H plus extra. And we're going to have to divide that by the total volume of the liquid, 0.060 liters plus 0.05 liters, okay, which is equal to, so this is our H plus concentration, 0.002 over 0.11, which is equal to 0.0182 molar. Okay, so now I can calculate the pH because this is my H plus concentration. So what I'm saying is I started out at a high pH. Okay, a high pH. I can't draw that very well. Let me erase that. I started out at a high pH, and I've already gone through the equivalence point, and now I'm down here in the acid region, in the H plus region, because now I have more acid than I had base. So I started out with base, and now I actually have an excess of acid. So now I can calculate my pH from the H plus concentration directly. pH is equal to the negative log of H plus, which is equal to the negative log of 0.0182, which is equal to 1.74. So we have a lot of extra acid, and now we've got a low pH. So hopefully that makes some sense. I'm going to try to get some more problems done here. Weak acid, strong base titration curve. Okay, so a 40 milliliter sample of 0.1 molar nitrous acid is titrated with 0.2 molar potassium hydroxide. So this is a weak acid, and this is a strong base. So for every 1 mole of potassium hydroxide, we're going to pull off 1 mole of hydrogens. Okay, so then we have to figure out how much we have left over of each thing and what region we're in. Okay, so in the first step here, we have to calculate, we have to do a stoichiometry problem. Then in the second step, we have to do equilibrium problem, because this has a weak acid. So if you have a weak acid or a weak base, you have to work an equilibrium problem in the second step. So we're asked to calculate the volume required to reach the equivalence point, the pH after the addition of 5 milliliters of KOH, and the pH at 1/2 the equivalence point. So I think I'm just going to go ahead and work this problem best I can, because this is an entire problem in and of itself. Okay, so the equivalence point occurs when the amount of acid and base are actually equal. Okay, so let's figure out how much we have. We have a 40. We have a 40 milliliter sample of 0.100 molar HNO2 okay, is titrated with 0.200 molar KOH. We don't know how much KOH was added, so we're asked in part A how much of this to reach the equivalence point. Okay, so the equivalence point is going to be equal when we have going to be reached when we have the moles of this equals to the moles of this. Okay, so first we're going to start by calculating how many moles of this we have, and then we're going to back calculate the amount of this to give us the moles. Okay, so start by calculating how many moles of HNO2 we have. We're starting with. So the moles of HNO2 is equal to 0.0400 liters times 0.100 moles per liter per 1 liter is equal to 4.00 times 10 to the minus third moles. Okay, so we need that much KOH to reach the equivalence point. So the volume of KOH is going to be, so KOH here is going to be 4.00 times 10 to the minus third moles, because we need exactly that many to reach the equivalence point. So what we're talking about is that inflection point here on our graph, the equivalence point. All right, times, and we have 2 moles per liter, 0.200 moles is 1 liter, that's our concentration, is equal to 0.0200 liters of KOH solution. Okay, so that's equal to 20 milliliters of KOH solution, this particular KOH solution at this concentration. Okay. All right, now part B says the pH after adding 5 milliliters of KOH. So we haven't added 20 yet. We're just going to add 5. And I've drawn my graph wrong. We're going from acid to base, so it goes this way, right? So we're going from acid to base, okay? At 20 milliliters, so here's our pH versus volume of base. Okay, so our equivalence point is somewhere around 7. Now this is a weak acid, weak base, so it's not going to be exactly 7. It's going to be a little off from 7. Okay. So because of the conjugate base in the solution. So at 20 milliliters, we've got the equivalence point, so we're only adding 5 milliliters. So we want the pH at 5 milliliters of base. Okay, that's our KOH. Okay, and so this is KOH. So the pH at 5 milliliters is going to be somewhere around here. Okay, so let's calculate that. So we know that we had how many moles of nitrous acid was 4.00 times 10 to the minus third. So that's 4.00 times 10 to the minus third moles of HNO2. Okay, and now we're going to be adding 5 milliliters of KOH. Okay, so we have to calculate the moles of that. 5 milliliters of KOH times 0.200 moles per liter, that's the concentration, equals 1.00 times 10 to the minus third moles of hydroxide. All right, so now we need to do a stoichiometry problem. And then we're going to work an equilibrium problem. So the equilibrium problem is usually done with the Henderson-Hasselbalch equation. Okay, so I've run out of room, so I'm going to have to go over to my extra space here. So 1 times 10 to the minus third moles of hydroxide, 4 times 10 to the minus third moles of acid. Okay, so we've got sodium hydroxide plus HNO2 goes to H2O plus NO2 minus. Okay, so we're going to do our stoichiometry problem. So we've got our before addition, and after addition. Okay, so that's 0 on the hydroxide when we get started. We've got 4 times 10 to the minus third moles of this. And I'm going to leave the sig figs off here because I don't have room. We're adding 1 times 10 to the minus third moles of this. Okay, so we're going to be subtracting the exact amount of hydroxide from the nitric acid because we've got a 1-to-1 ratio here. This is a one-way arrow, so we're going to be taking this many H pluses off. Okay, so we're going to have 3 times 10 to the minus third moles of acid when we're done. All right, and then we're going to have 1 times 10 to the minus third moles of NO2 minus when we're done, okay, because we're increasing this NO2 minus for, stoichiometrically. Okay, so now we've, after the addition, before this thing starts equilibrating, we've got that. So now we can solve for the pH. We wanted the pH after the addition of 5 milliliters. So pH is equal to the pKa plus the log of base over acid, which is equal to, the pKa for this is 3.34, plus the log, it's almost time to go, of 1 times 10 to the minus third over 3 times 10 to the minus third, okay, which is equal to 3.34 minus 0.48, which is equal to 2.86, okay? So our pH in this case is equal to 2.86. All right, and so now we want the pH at 1/2 of the equivalence point. At 1/2 the equivalence point, okay? So at 1/2 the equivalence point, the amount of added base is exactly 1/2 the initial amount of acid, okay? The base converts exactly half of the HNO2 into NO2 minus. So let's look at that. OH plus HNO2, I'm going to go ahead and finish this up real quick, goes to H2O plus NO2 minus, okay? So we're starting out with no hydroxide, and we've got 4 times 10 to the minus third moles of this, okay, and we've got 0 moles of this, and then we're adding 2 times 10 to the minus third moles of this because we got 1/2 of the equivalence point. So we're adding half of the hydroxide here that it takes to neutralize the acid, okay? So we're going to end up with 2 times 10 to the minus third moles of this, okay? So we've got equal amounts of this at half the equivalence point because half of this has been neutralized. And also we've got 2 times 10 to the minus third moles of the NO2 minus as well. So pH is equal to the pKa plus the log of the base over the acid. And here's our conjugate base, okay? This is going to be, so we're adding 2 times 10 to the minus third moles of hydroxide. So we're going to end up with no hydroxide because it completely reacts. Our conjugate base is the NO2 minus, that's this, and our acid is this. So that's going to be equal to 3.34 plus the log of 2 times 10 to the minus third over 2 times 10 to the minus third, which is equal to 3.34 plus what? Plus the log of 1. And so that's equal to 3.34 plus what's the log of 1 is 0. Okay, so notice that the pH at half the equivalence point is equal to the pKa, and that's a trick. At half the equivalence point, the pH is equal to the pKa. So in this case, we've got a curve that looks like this. Oh goodness, I don't know why I did that wrong. A curve that looks like this. We're going to be starting out with a low pH, okay, and going to a higher pH. And at half the equivalence point, at half the amount of base that it takes to neutralize this, the pH is equal to the pKa, okay? So that's all I have time for today. We'll continue with 18.7 next time. And I'm going to take my computer in to get it looked at today, so hopefully they can fix my writing problem. And so I will catch you on Tuesday. Do I have any questions before I let you go? I'm going to go ahead and stop the recording.